presentation will be Associate Professor Miguel Bordallo Lopez from, he's one of us, so from University of Oulu, from Center for Machine Vision and Signal Analysis, leads the strategic research area for distributed intelligence. His current focus on the convergence of computer vision and telecom using real-time video analysis and radio signals to sense humans. So he will be talking about the convergence of computer vision and communications. Go ahead.
Okay, thank you for the presentation. So when I was invited to give a talk here, I was given freedom to talk about almost anything I wanted. And I thought at the beginning that I was going to discuss this distributed intelligence and all the research that we have been doing in Oulu. But I thought I would use the opportunity to make some kind of statement of how computer vision and telecommunications are slowly becoming the same thing, and how computer vision is going to be an essential part of future communication research and development. And I will try to explain why I believe that. So it's possible to argue that both wireless communications and computer vision have been evolving as distinct fields. Even in our department, we are in 2 different floors, and we only meet sometimes in the elevator. So if we talk about wireless communications, we can see that we started trying to connect people by voice calls, and then we were moving to more rich data, then just to all types of data. And now I think in the last couple of generations, we are moving just from transmitting data to try to transmit what we see, and maybe even now what we understand. If we go on computer vision, it started with the mission of understanding the world through what we see with cameras. So we started with very simple shapes, recognition of shapes. We moved to the object detection, more complicated objects and their interaction, like, for example, all this face recognition, face analysis, all type of stuff. It came deep learning. Now we could throw massive amount of data into models and try to learn every single type of correlations and what they have. And I would say that the latest emerging thing is this vision foundation models, which are able to, in a large scale, you can basically send what you see, and they are able somehow to explain what is there. So basically, they tell you everything about the scene. So the needs of 6G is to understand the world, and this is what matching vision or computer vision provides. The needs of computer vision now is how can we distribute these big vision models all around the world. So I think we are doomed to actually converge and start doing the same thing. So I would say that the convergence happens at several levels. So it's a data level, algorithmic level, hardware level, application level, and they will become an ecosystem. I'll try to go through each one of them. So at data level, that I could say almost the physical level, in telecommunications, we are going to higher frequencies. At higher frequencies, the radio waves start behaving a little bit like photonics, a little bit like the light, not exactly. At the same time, in computer vision, we're exploring things that are beyond visible light, going far into the infrared as much as we can. So basically, we are going down in the spectrum. Telecommunications are going up. There are a couple of times that we have tried to jump. In computer vision, we have been trying to analyze sub-Earth images. In telecommunications, you can say that there is visible light communication, that they use visual spectrum to try to do communication. So at the physical level and the type of data that we get, we are slowly getting there. At an algorithmic level, when we talk about the needs of 6G applications, we are talking about localization, where the user is, mapping, where am I in the context, and even reconstructing the environment. So typical algorithms for this are the SLAM, simultaneous localization and mapping. This has been traditionally done with computer vision with cameras. Now there is this radio SLAM. They try to reconstruct the environment in the same way using radios. Distributed and collaborative algorithms. So algorithms for telecommunications were aiming at distributed information. Algorithms for computer vision were mostly centralized. Now they need to be distributed. We need all these distributed algorithms that are collaborative, both fields. And then we are all the time talking about more dynamic, adaptive environments and algorithms. So in computer vision, we want to understand change as fast as possible, even preemptively. The same in communication. So at algorithmic level, we are going the same type of ways. at the hardware level, I'm talking mostly here about computing rather than sensing hardware, but we have the basic unit of computation in telecommunications is the system on chip, and I would say that for computer vision is becoming the same way. So this heterogeneous multiprocessor that they have sensor processors, AI processors, DSPs, GPUs. We are slowly, if we are able to give access to all these processors to both applications at the level of computer vision and communications, they can be reused fairly easily. They are the same type of computations. Basically, it's matrix multiplications, multiplication and accumulations, filtering, same type of operations. Edge to cloud computing, distributing all these computations from centralized clouds into the all this continuum, all the continuum of possible computations. And finally, integrated sensing and communications, and even a new paradigm that is emerging where you try to do ISAC and learning at the same time. They are the hardware is already being shared by this type of applications. And at an application level, okay, I didn't go to the metaverse. I went just to mostly this collaborative telepresence, maybe something for telcos of now. But the applications of 6G, if we try to think all these use cases, most of them what they need is that we are able to process lots of streams of videos and make intelligent analysis of them in a synchronized manner in real time, very fast, instantaneous. And this is why we need mostly now the capabilities, even virtual reality, artificial or augmented reality, they need basically to process video very fast, low latency, project radios at the same time. When we talk about for what we need computer vision, we need to understand the environment, understand what we see, what we don't see, what's going to happen. So for example, we could analyze the networks through this. So I would say that if we start developing these things together, then we are in the same ecosystem. We can start even trying to think some joint business models. So for example, we can consider aggregation and personalization of data. As we move, we are personalizing the data of the sensors in the way that we perceive them. We can donate our data as well to others and create maps of information. If it's in a privacy manner, there is some incentive for installing this type of sensors and to share this type of sensors if we can sell this information for personalizing for the people. Semantic slicing, we get sensors that only transmit what we mean or what we want to see, and they keep the other information. And of course, all type of map building. So as I say, all this is happening at all these levels. And if we start developing all together at the same time, then two paradigms emerge. First one is view to communicate, quite simple. We use vision to learn how to communicate, communicate to view. We use communications to learn how to view. So to try what they mean. So in view to communicate, the whole point is we could improve data transmission if we know how it's happening. So for that, we require mostly two things. Accurate mapping, knowing how the environment looks, and the electromagnetic properties of the material. And that way we can start enabling, because we know how the signals are propagating, we could enable non-line of sight communications, multipath transmission, and we have impacts in all type of network applications. For example, this is a visualization tool for radio signals that ray trace how they are propagating. So we actually know what's in a fairly complex environment, how the signals are arriving. This is work that we've been doing. Building these maps is not easy, but now there's a lot of advances in the last year. So now we can build very fast maps quite fast. This is a map of the University of Oulu. It's only one building and it's almost 1 kilometer from one side to another. And we were able to collect this in a couple of hours just by walking with a Kinect, and then a few hours for rebuilding the whole environment. The problem is it's basically a geometric model of the environment that gives us visual information, so colors. This doesn't help for the radio spectrum. We have to move from 3D to what I call 5D. We have to incorporate at the same time as we are collecting this data, information in other parts of the electromagnetic spectrum that are useful for communications, and we need to add some kind of dynamics into that. So basically temporal structure. And I don't think the way is, of course, at the beginning, we can have a person walking all the world or a car walking all the streets, but essentially distributed modeling is needed. So we need to get information from all these sensors at the same time to re-reconstruct the environment several times, and telecommunications are needed for that. Once we have all these maps, then we can predict and interpret the environment. So computer vision reconstruct environments. The cameras are acting as sensors for real-time data collection. Now we can anticipate obstructions, not only see the obstructions. There's not only a car that is there that is obstructing my signal. I know the car is moving, the car will come, and I can already preemptively adapt. So basically, I can even simulate what's going to happen in a simulator and then make the network adapt. So it's moving from reactive networks into proactive networks, thanks to computer vision. The other paradigm, the other way around, communicate to view. How can communications help to view? Well, most of the cameras that we have now, even when you have these depth cameras or several cameras, they are still mostly monocular. That means that getting distance and depth is an ill-posed problem. So telecommunications are very good at measuring, or you can be with radio signals measuring delays using radars, or maybe the distance between a transmitter and a receiver. So if we have a monocular image, you can see up there in the corner, and we add a few priors of distance measured with other device, you can reconstruct the environment in a much better way. So for example, the one that you have in the middle has gotten 12 distant measurements done with a radar, and the one on the right doesn't. And it dramatically improves what we understand of the environment just with a few references of depth. Also, communications and radio signals can help us see around the corners. It will take a little more than 3, sorry. So to see around the corners, humans can already see around the corners if we think. If you think of a corridor that is completely dark in one side and makes a corner and then is illuminated, as a person is approaching in the illuminated part, you see some differences in the shadow, and you can already know that something is coming. In the same way, you can see these distortions in the radio wave. The main point of the radio wave is if we can actively steer and learn sensing strategies to see around the corner, and we can use other information that we have from that corridor when it had light to actually reconstruct what's going on. So basically increase situational awareness. Seeing through walls, it seems much more complicated, but in practice, it means being able to connect to sensors as you walk and project the information that you need to have. So basically, it means seamless visual coverage, because you are able to connect to cameras or to models that are far away from where you are. And so these are the paradigms of the things that can be investigated now. So how do we do them? So there are tools available and in development. We are working in a few of them. So basically, you have this camera-aided base station and the camera-aided intelligent surfaces. The point of the camera is twofold. In one of them, you can use them in conjunction with the radio signals to increase or to improve how they work. In another way, you can use the camera at the beginning to train models of how the radio is behaving. And then at some point, you can switch off the camera, but you learn particularly that environment sometimes. Doing this in the real world is very, very tough. It requires a lot of experimentation and a lot of data collection. I believe that this can be done quite a lot in simulation. We build realistic models, and then we simulate densely all these scenarios and start from a model that already exists. And there's a need of making machine learning exactly for this type of radio understanding. And we are working on all of this. And at the same time, we need to build experimentation environments. So in all, we are building a couple of them. This is a convergence chamber and digital twin. It's a real chamber where we are going to build all these tools during next year. So maybe by mid or the end of 2025, it will be ready and accessible as a European infrastructure for all. And at the same time, we are constructing a digital twin of it, so you can simulate all these experiments in the room before you go there, and then make real measurements and see how they matter. And at the same time, we have this small multimodal sensing lab where we have a lot of sensors, cameras, radios, radars at the same time, and we are collecting data all the time and making models of the environment. So these experimental environments are needed. There are a lot of challenges that are not related maybe to science, but to engineering, system integration, demonstration of use cases, data representation and multimodality, device synchronization. I have seen many cases where you have a wireless link separated 100 meters or 20 meters that goes very fast, but then you need to have a cable with a clock from one to another so you can synchronize both of them. This is not wireless anymore. And then, of course, as we are developing this type of applications, there are a lot of side effects of things that can be done that we don't intend to do, but other malicious actors could do. Problems with privacy, ethics, sustainability, they need to be addressed. So very fast, because they've been talking about this before, the three low-hanging fruits for me in the application space. In the automotive, now we are talking vehicle-to-vehicle communication, but it's about where they are and where they are going. I think understanding what one vehicle is understanding or seeing should be transmitted to the others as well. This is vision, basically. In healthcare, real-time, high-resolution imaging, in telemedicine and remote diagnosis, a lot of things can be done from far away. And in manufacturing, understanding how the manufacturing plant is working. So last 10 seconds, takeaway message. There's a new paradigm in research where computer vision, in my opinion, should be included in any telecommunications research or project as one building block. Hopefully, all agree. There are already tools available in development, so we are not starting from zero. There are substantial challenges ahead, but they're mostly engineering, so they are ones that are nice to tackle and to work together. And I think there's possibility of making potential impact in applications right away. So